Hi everyone. In this video we're going to be talking about the first derivative test and the second derivative test. We've seen all of these before already, so it shouldn't be anything terribly new to you. But basically, here's the deal. With the first derivative test, we can figure out if our function is increasing or decreasing, since the first derivative tells us about the slope of the tangent line of the function. Whenever the slope of that tangent line is positive, our function's increasing. Whenever the slope of that tangent line is negative, our function's decreasing. So the first derivative test tells us if f prime of x is greater than 0, then f of x is increasing. And if f prime of x is less than 0, f of x is decreasing. Oftentimes we use this test to find, when f prime of x is equal to 0, because that's a point right in here that we don't talk about, what is happening? And so there are a couple of things that could be happening there, right? Let me show you an illustration of this function. If I want to think about what f prime looks like, all I have to do is sketch in the slopes of some tangent lines. So the slopes are very, very steep and negative here. They get less negative. They actually flatten out perhaps to 0 there, but then go back to being negative, flatten out again, and then turn positive. So my derivative is negative all the way here. It's 0 right here. It's negative again until there. It's 0 right there. And then it becomes positive. So we'd say here, right, our function is decreasing. It's neither increasing nor decreasing actually right at this point, but then it's decreasing again, turns, and begins increasing. Okay. And now the interesting thing is, we usually use when the derivative is equal to 0 to tell us about if it's a maximum point or a minimum point, but we have to be really careful here. So I'm going to write this in red. F prime of x equals 0 does not mean x is a max or min. It does not mean that. And this is the exact situation for where we see it. F prime of x is 0 right here. But this is neither a max nor a min, since there are points above it, just to the left, and points below it, just to the right. It can't be a max or a min. It's important that this doesn't dictate whether it's a max or a min. Instead, this one does, and the big difference is that at this point, f prime is changing signs. It's going from negative to positive, which means it has to turn at some point. Here, f prime is going from negative and staying negative, so our function doesn't have to turn. Okay? It is very, very, very important. This subtle distinction, when this is 0, it doesn't always mean that we have a max or a min, even though it often means that from the problems that we've been doing. Okay. A way to test this out is to use what we call the second derivative test. So let me just move this a bit. The second derivative test tells us whether or not we have a max or min based on the second derivative. So if f prime is 0, and f double prime is positive, well, we saw that f double prime means concavity. It tells us about concavity of the function. Sorry, it doesn't mean concavity, but it tells us about the concavity of the function. If the second derivative is positive, that means we're concave up. So if we're concave up and the first derivative is 0, then f itself is at a local minimum. We're concave up and the derivative is 0. Similarly, if we're concave down and the derivative is 0, then f of x is at a local maximum. So we can use this second derivative test rather than using these sign lines that we've been using if we want to figure out whether or not we're at a max or a min. The second derivative test in general just like the first derivative test, has these two stipulations, right? One, f double prime of x being greater than 0 means f of x is concave up. And 2, f double prime of x being less than 0 means f of x is concave down. And if you don't happen to remember these, you can always think that this is the rate of change of the rate of change, right? So if your rate of change of your rate of change is positive, let's look at this particular interval here. You're getting more and more steep, so you have to get concave up. But if the rate of change of your rate of change is negative, you'd be getting less and less steep. You'd be concave down, something like that. So another way to think about it. I'm going to go through two problems with you here. One problem being a very algebraic problem, and then another problem being a graphical problem. And we're going to apply these tests to both of them. One last thing before I fully erase the second derivative test. Sorry about this. Just like we saw that the first derivative, being 0, doesn't really guarantee us anything, but when it changes signs, it does guarantee we're at a local extrema. So too here, when f double prime changes signs, when this happens, when f double prime changes signs, well, that means that we're going from positive to negative or from negative to positive. That means concavity changes. This, right here, when this changes signs, is when we have a point of inflection. Oftentimes, to find that, again, we set it equal to 0, but then we have to test points around the x values that we find to make sure that it is, in fact, changing signs. Again, the same danger as with the first derivative test. And let's take that moving forward. So, all of that being said, here we go with our first function. And our first function is going to be half of x is equal to the square root of x times natural log of x. Now, if you're like me, you have no idea what this function looks like, and that's just fine. Let's say that we don't have a calculator. That's okay too. If you wanted to play around a bit and try to figure out what it looks like, you can always make a table, pick your favorite x values. Maybe we pick 1 or e squared or whatever you want to pick. Throw them in there, see what you get at for a y value. The one thing that is important to note about this function is that natural log is not defined everywhere. So in our minds, we know that in this particular function, x has to be greater than 0, because natural log is not defined for any numbers less than or equal to 0. So my goal in this particular problem is to find 1, where is f increasing or decreasing? 2, any local extrema? And 3, where is f concave up or down? These are the 3 things that I'm going to try to find with this function. Now, this whiteboard is going to prove to be a bit too small to do all of this, but hopefully we can fit it in. I'm going to erase this as a result, though. I'm also going to erase x is greater than 0, but we'll keep it in our minds. Hopefully it's down in your notes. And away we go. So we recall that the first derivative test tells us whether or not our function's increasing or decreasing, and to figure this out, we need to take the derivative. So that seems okay. If the derivative is positive, we're increasing. If the derivative is negative, we're decreasing. So let's test this out here. F prime. All right, good old product rule. Derivative of square root x, well, that's x to the 1/2, so that means it's 1/2 x to the negative 1/2 times natural log plus, well, natural log's derivative is 1 over x times square root x. And maybe we'll tidy this up a bit. So x to the negative 1/2 is 1 over x to the 1/2, which is 1 over square root x. So this is 1 over 2 roots x times natural log x. and this is root x over x. And let's keep tidying so that we make this a bit better for us as well. This is going to be natural log x over 2 root x. Okay, let's think about this one for a second. This is x to the 1/2, and this is x to the 1. When you're dividing same base, different exponent, you subtract the exponents. That makes this x to the negative 1/2, which makes it 1 over square roots x. And because of all of this, I can make these have the same denominator by multiplying the top and bottom of this right fraction by 2. And I'll get natural log of x plus 2 all over 2 root x. And this is what f prime is equal to. Here we are, great. And now you're probably wondering to yourself, well, great, what am I going to do now? Because all of these are ugly, except maybe for this 2. How am I going to figure out if it's positive, negative, or neither? Well, what we're going to do is we're going to set it equal to 0. Because this function is a quotient of continuous functions, we know that it's continuous everywhere it's defined. And so we remember that, oh, right, it's not defined when x is less than or equal to 0, but if x is greater than 0, this is defined everywhere, and so it has to be continuous. Because it has to be continuous, the only spot at which it can change signs is a spot where it crosses the x-axis. So we have to figure out when this derivative is equal to 0. So let's do that. Let's say ln x plus 2 over 2 root x is equal to 0. Well, if this is equal to 0, I can multiply both sides by 2 root x, cancels out this denominator, I get natural log x plus 2 is equal to 0. Okay, and that's not so bad. That means, oops, sorry, I'm running out of board space already. Natural log of x equals negative 2, and we remember how natural logs work. This is log base e of x equals negative 2, so that means x had better equal e to the negative 2nd power. And this is the only value of x that can possibly be a place where the derivative changes sign. There are 2 ways to test if the derivative equaling 0 gives us a max, min, or neither. One way is with a sign line, which we've been doing. The other way is by finding the second derivative, and then using the second derivative to figure out if it's concave up or down, and using the concavity in conjunction with this fact that that the first derivative is equal to 0 to figure out if it's a max or a min or neither. For this one, I'm going to start by making a sign line, and then I'm going to confirm my result by taking the second derivative and testing that out. So let's do this here. Here comes my sign line, and this sign line is representing f prime. We know it at 0 is where we start. And we can't equal 0, so I'll put an open circle right at 0. Can't possibly equal 0. Our only critical value for x is e to the negative 2nd power. And that's pretty small positive number, right? E is like 2.7. This is e to the negative 2nd, so it's maybe like 1/9. It's a pretty small interval here. And then the rest of f prime is going to be all the same. So let's think for a second here. Here's our derivative expression. I can pick a value in between 0 and e to the negative 2nd. Perhaps I'll pick the value e to the negative 3rd. And you might be thinking that's a strange choice, but because I have a natural log in here, I want to pick a value that will give me a whole number out. I'm sorry, an integer value out. So if I pick e to the negative 3rd, f prime of e to the negative 3rd, well, that's ln of e to the negative 3rd is just negative 3. And square root of x is always positive. So I don't know what this is, and I don't really care. It's some positive number. But I do care that my numerator is negative. Because my numerator is negative and my denominator is positive, this has to be negative. Has to be negative. Okay? Next, I have to figure out, well, what's going on here? Am I still negative? Have I switched to positive? These are my only 2 options. And so let's pick a number out here. And maybe I'll pick e. Again, because I want this to be a nice value here for my natural log. Natural log of e is just 1. 1 plus 2 is 3. So I get 3 over, again, some positive number. And that makes this positive here. So my conclusion is that f prime changes sign from negative to positive at x equals e to the negative second power. This means that I definitely have a local extrema, and because it goes from negative to positive right there, it has to be a local minimum. So f has a local min at x equals e to the negative 2, since f prime of x goes from negative to positive. Great. Okay. So maybe some of the algebra you weren't thrilled about, but the concept here is the big one, right? Here, our function is decreasing. Here, our function is increasing. Since it's going from decreasing to increasing, at that point, it has to be a local minimum. But this also tells us, here's our interval here, 0 to e to the negative second, and on this interval we're decreasing. And here's our other interval here, e to the negative second to infinity, and on that interval we're increasing. Great. So I've answered a couple of the questions so far, and let's continue answering them. So let me write down this final expression, which was my f prime of x. I'm just going to save that right here. F prime. That was equal to natural log x plus 2 over 2 square root 6. Great. Because remember, I still need to find out concavity, and I want to apply the second derivative test and confirm that I was correct in saying at e to the negative second power, this is a local minimum. Great. So, time to find f double prime. And if you thought finding f prime was bad, you're in for a treat, because f double prime, to find it, we need to use the quotient rule. So, the quotient rule is the bottom times the derivative of the top, bottom times the derivative of the top, minus the top times the derivative of the bottom, derivative of the bottom, all over the bottom squared. From here, I'm just going to tidy up, just like I did with the first derivative. 2 root x times 1 over x is 2 over root x, just like we saw with the first derivative. Okay, so I'll move this into the numerator. These 2's will cancel. I'll get ln x plus 2 all over, just plain old square root x. Okay. And then I'll have to figure out, my denominator is just 4x. Right? Great. So, next step, I have to combine some like terms here. 2 minus ln x minus 2 just gives me negative ln x over root x. And that's all over 4x. Yikes. And maybe you don't love fractions in fractions. I don't love fractions in fractions, so I like to rewrite this. Since I'm dividing this fraction by 4x, it's the same as multiplying by 1 over 4x. And that makes it a little bit easier for me to see what's happening here. And so I end up getting negative ln x all over 4x to the 3 halves. That's my second derivative. Not the, well, actually, maybe a little bit prettier than that one, depending on how much you liked that one. So here's our second derivative. Oops, f double prime. And again, x has to be greater than 0, since natural log and 4x to the 3 halves are both continuous on that domain. F double prime is going to be continuous. So, when is this changing signs? It's only changing signs when this function is equal to 0, potentially, right? It might not even, but if it does, it has to be when the second derivative equals 0. If this fraction equals 0, that means the numerator equals 0. So when does natural log of x equal 0? Well, that happens only when x equals 1. So x equals 1 is our critical value here. And so again, to figure out concavity, we can make our nice little sine line over here. It'll start there, and it'll keep going that way. It'll have an open circle at 0 because it's not defined there. It'll have a critical value at 1. And let's see here. I want to figure out when this is positive, when it's negative, when it's neither. So let me plug in some values here and see what happens. If I plug in a value between 0 and 1, natural log is going to be negative. Since I have negative natural log, that makes the numerator positive. The denominator is always positive, since x is always positive. So positive over positive, this gives me positive. If x is bigger than 1, let's say x is e, for instance. Natural log of e is 1. That's negative 1 as my numerator. My denominator is always positive. This is going to be negative. So the only point at which my second derivative changes sign is the point x equals 1. This means x equals 1 is a point of inflection on my graph. So if I asked you, what are the points of inflection? And here I'm asking for the point of inflection, not just the x value of it. The point of inflection would be when x equals 1. I plug this into my original function. That's 1 times 0. So the point of inflection is 1, 0, because f double prime of x changes sign from plus to minus at x equals 1. Okay. And let's use this sine line to confirm that we do in fact have a local minimum when x equals e to the negative second. So remember, to be a local minimum, our first derivative is 0, and our second derivative is concave up. E to the negative second is more than 0, but less than 1, so we're in this region. That means we're concave up, and that's awesome, because we need to be concave up in order for that to be a local minimum. The last thing is just our intervals of concave up and concave down. So we're concave up on the interval from 0 to 1, concave up. And we're concave down on the interval from 1 out to infinity. Okay. So this was a quick recap of the first and second derivative test, just done algebraically. Whew, thanks for bearing with me. That was a 20-minute algebra problem. Now we're going to continue these tests, but to do them graphically. So this video is going to be a little long, but that's okay. Hopefully most of it's review for you. There was a lot of algebra in that particular problem, but we'll get tons more practice with that over the next couple of months. So as long as you're able to follow along with the big idea of calculus, then that's really great for right now, and we'll just continue fine-tuning the algebra over time. So let's look at a graph. Here's a graph. I'm going to sketch a function for you, and that function's going to be f prime. And maybe it'll look something like this. Whoop. Whoop. Great. So there's my function. And let me label some x coordinates for you here. This will be -2, -1, 0, 1, 2, 3, and 4. Great. So my interval is from -2 to 4. And the questions are, where are my maxes, where are my mins, where am I increasing, where am I decreasing, where am I concave up, where am I concave down? Same exact questions as before. So there are a few ways that you can do this. What I'll say is, we'll start with everything that the first derivative tells us. So we recall that if f prime is positive, f is increasing. And this occurs, well, from -2 to -1. At -1 it's 0, so that doesn't quite work. But then from -1 all the way to 2, we're still positive. And then another interval here, from 3 to 4, we're also still positive. Make that an open circle. Great. Next, when f prime is negative, we know our function is decreasing. And this only happens once on this interval, and it's from 2 to 3. So I have all of these guys. If I wanted to find a maximum or a minimum point, I'd have to test, since this is on a closed interval, I have to test both the endpoints and also the points where f prime changes signs. So the endpoints of this interval are -2 and 4. And then f prime changes signs twice, once at +2 and once at 3. Okay. So let's see what happens here. At -2, as I'm moving to the right, my function is increasing. So as I move to the right, my function's increasing. That means -2 could be a local minimum, right? Since my function starts out by increasing from that endpoint. Now let me test my other endpoint here, x equals 4. Well, at x equals 4, as I'm heading towards 4, I'm increasing all the way up until 4. Increasing all the way up until 4, so that makes this a local max. The other points, remember, are only the points where f prime changes sign. So -1, get out of here, don't change sign there. X equals 2, this goes from increasing to decreasing, right? From a derivative that is positive to a derivative that's negative, so up to down. That makes this a local max. And x equals 3, the derivative is negative, jumps up to positive, so that makes this a local min, because we're going from negative to positive. Next, we want to test the concavity, and we want to use the concavity to confirm that all of these things are correct. So let's find that out. If I want to find the second derivative of the original function of f, the second derivative is the derivative of the first derivative. So in this case, it's just the derivative of this red curve that's shown here. Now, you might notice that the tangent lines start out negative, they flatten out to 0, they turn positive, they flatten out to 0, they turn negative, and then they stay negative. So, if I'm writing this out for myself, I'll just make a little chart inside my graph. Okay? And in blue, I'm going to represent f double prime. F double prime is negative here, it's positive here, it's negative there, and it's negative there. So, f double prime changes signs right here at -1. It changes signs right here at 1, and that's it. Those are the only two spots where f double prime changes signs. Even though here you have a jump across the x-axis, that's a jump with f prime, not with f double prime. So my points of inflection are when the second derivative changes sign, and that happens at -1, and also +1. And we should be able to confirm that these things are true based on the second derivative again. The endpoints we already dealt with. The endpoints have to be all set. To say that 2 is a local max means that our derivative should be 0 and we should be concave down. And that is true. We're concave down right there. For this to be a local minimum, well, it's tough because we're actually not defined on that one. So f prime is not even equal to 0, so we can't use the second derivative test there. But that's okay. We still have our intervals here of concavity. Concave down from -2 to -1. Concave up from -1 to 1. Concave down again from 1 to 3. And then concave down again from 3 to 4. So that's graphically how we can attack one of these problems. If you were asked something like, what is the absolute minimum or the absolute maximum on this interval? Again, we could try to tackle that. You might need some more information to be absolutely positively sure, but based on this particular graph, since -2 is a local minimum, and then 2 is a local maximum, we're increasing on this entire interval here. Since we're increasing for such a long time, it would be a good guess that 2 is our absolute maximum. Because after 2, we decrease for a while and then increase for a bit. And those might cancel each other out. They might not. It is hard to tell from this graph. If you wanted to find the absolute minimum, we can be a bit more sure here, because -2, afterwards you're increasing for so long. And then from -2 to 3, you're decreasing only for a short amount of time. So -2 is most likely our absolute minimum here. But this is the first and second derivative test, both algebraically and graphically. Remember, it's just the big idea that whenever the derivative changes signs, we could have a max or a min. Whenever the second derivative changes signs, we have a point of inflection. And to do that algebraically, we oftentimes take the derivatives and set them to 0 and solve, but then we have to show that they change sign. If we don't show that, then we haven't shown anything. Alternatively, instead of showing that they change sign, you can use the second derivative test of concavity to show that you have a local min or a local max. So thanks so much for watching, and hopefully this review was helpful.